Hey there, folks. I'm going to walk you through a little lesson in half-life. This is part of our nuclear chemistry unit, Unit 10. Okay, so first I got to tell you about something crazy. We've been keeping this a secret all year. The idea is transmutation. It turns out in nuclear chemistry, one element can actually turn into another. For example, this radioactive uranium-238, would be a common isotope, can actually turn into the element thorium. Notice uranium has an atomic number of 92, thorium has an atomic number of 90. These are two different elements, but uranium can turn into thorium. How? By radioactive decay. It turns out that uranium is very unstable. Okay, so in this diagram here, we're showing the parent nucleus of uranium-238. It's unstable. It has probably too many neutrons. Okay, the nucleus has neutrons and protons, but it has too many neutrons. And to become more stable, it will get rid of some neutrons and protons in what's called an alpha particle. You may have already learned about this, or you'll learn about it next week. And when it gets rid of an alpha particle, it becomes more stable. So we start with something that is unstable or radioactive, and then we end up with something that is more stable. It might still be radioactive, but at least it's a little bit more stable. But notice, so alpha radiation is emitted. What are alpha particles? Again, you may have learned about them already, or you may learn about them next week. It's just a type of radiation. It's this particle made of 2 protons and 2 neutrons. Notice now the nucleus of what we started with as uranium has fewer protons. And so now it actually is a different element. It is the element thorium with an atomic number of 90. This is transmutation. One element can turn into another. By doing so, it becomes more stable. And then that thorium, if it is still radioactive, it could become even more stable by going through transmutation to become another element. But we're just going to focus on something simple like uranium turning to thorium for now, okay? So now that brings us to the idea of half-life, which you heard about in earth science. Half-life, the definition is the time it takes for 1/2 of your parent isotope, like your uranium, to decay to your daughter product, your thorium. And so in this case, uranium gives off alpha radiation and produces thorium, the daughter product. You can think of it as uranium breaks apart into some alpha radiation that's emitted. That's that thing with 2 protons and 2 neutrons. And the daughter product is what is left behind. So uranium breaks apart into the thorium daughter product by giving off alpha radiation. So what does half-life have to do with this? Well, basically, let's think of an example. In this example, we're just going to do a really simple half-life. Let's say we've got some kind of radioactive isotope with a half-life of 10 years, okay? And so that radioactive isotope, those are unstable nuclei, and they are going to go through some transmutation. They're going to go through radioactive decay. So if we start out with 100% of our parent isotope, after 10 years, we will have 50% of our parent isotope left, and 50% will have been turned into the daughter product. And then if another half-life passes, another 10 years, we will now have 25% of our original parent isotope, and 75% of our substance will now be daughter product. And we could go another 10 years, then we'd get down to 12.5% of our original parent isotope and some whatever adds up to 100% of the daughter product. So again, half-life, the time it takes for 1/2 of your parent isotope to decay to your daughter product. Let's look through a couple examples. Table N has a list of a bunch of different naturally occurring radioactive isotopes. It lists their half-life in either days or years or milliseconds or minutes or seconds, etc. Decay mode, you might have learned about already. You might be teaching yourself from the hyperdoc. You might learn about decay mode next week. It just means what type of radiation is emitted. Anyway, cesium-137. Cesium-137, apparently we're starting out with 80 grams of cesium-137, and it has a half-life of what? Oh, right there. Cesium-137 has a half-life of 30.2 years. That means after 30.2 years, we'll have only half of our original cesium-137. So how long will it take, is the question. How long will it take for 80 grams of cesium-137 to decay down to 10 grams of cesium-137? Well, here's how you do it. You don't even have to use a formula. You just have to divide by 2s. Okay, 80 grams will become 40 grams after one half-life. 40 grams will become 20 grams after another half-life. 20 grams will become 10 grams after another half-life. And each half-life for this isotope is 30.2 years. So the answer, how long will this take, is 30.2 years for the first half-life, 30.2 years for the second half-life, 30.2 years for the third half-life, and now we're at 10 grams. Add those up, we get 90.6 years, or 3 times 30.2 equals 90.6 years. Remember, each half-life is one of these hops, going from our start to the next phase, to the next phase, to the next phase. Let's have a look at another example. Carbon-14. Carbon-14 has a half-life of what? Oh, right there in table N. Has a half-life of 5,715 years. 5,715 years is the half-life of carbon-14. So the question is, what fraction of C14 remains unchanged after 11,430 years? How do we do this? Well, first we have to say, okay, how many half-lives is that? 11,430 divided by 5,715 is 2 equals 2. So that's 2 half-lives. Okay, so let's say we start with 1 whole of C14. After 1 half-life, we've got a half of our C14. The fraction left that's blue, that's our parent isotope, is 1/2. After 2 half-lives, a half becomes a quarter of our original fraction. And so the answer is, after 2 half-lives, 1/4 of our original parent isotope will remain. Let's try one more example after we just remind you again the definition. Half-life, the time it takes for 1/2 of your parent isotope to decay to daughter product. Starting out with 100% parent isotope, after 1 half-life, whatever time that is for whatever element you've got, you'll have 50% of your parent isotope. Okay. A couple of more practice questions. What is the total number of years that must pass before only 25 grams of an original 100-gram sample of C14 remains unchanged? So we start out with 100 grams, we get to 25 grams, how many half-lives will have passed? To do this, you really don't need a formula, you just got to do something like this little diagram I'm making here. Starting out with 100 grams, after 1 half-life, we're at 50 grams, okay? 1 half-life takes us from 100 grams to 50 grams. Another half-life takes us from 50 grams to 25 grams, and hey, now we've reached our end point. So the answer is 2 hops or 2 half-lives, or 11,430 years. Okay? Each half-life knocks it down to 1/2 of what you had previously. Try one more question about carbon-14. A sample of wood is found to contain 1/8 as much C14 as is present in the wood of a living tree. What is the approximate age in years of this sample of wood? So we got carbon-14 with its half-life of 5,715 years. We start out with 1 whole, okay? And then after 1 half-life, we've got a half of that amount. After another half-life, we've got a quarter of that amount. After another half-life, we've got an eighth of that amount. So 5,715 for the first half-life, 5,715 for the second half-life, 5,715 for the third half-life will equal 3 times 5,715, or 17,145 years. So to go from 1 to 1/2 to 1/4 to 1/8, that was 3 hops, 3 times the half-life time for carbon-14. All right, folks, thanks for listening, and we will see you in class or in the next meet or in the HyperDoc.